Hi guys, and welcome to today's video on modeling geometric growth and decay. Wow, hold on a moment. Geometric growth and decay? What was all that about? What is all that about, he says, and getting that all sorted for you now. In previous videos for this further math scheme, we've been looking at linear growth and decay. That's where we add on or take away the same value from our investment or our loan or whatever it is we were dealing with. Hate to tell you this, that nothing in life is simple. You see what I did there? Nope, it was bad, wasn't it? Yes, it was. We're now going to sort of ramp up the complexity just a little bit. But the good news is, the basic formula we've been using in the previous videos, you've been watching the previous videos? Hopefully you have. Actually is fairly much or very much the same. We're just tweaking bits. So your formula books or your summary books or whatever you're going to take into an exam with you is going to be freaking awesome because you're just going to have the page of the same formula, really. Now, my name is Darren, otherwise known as MaffsGuru, and thank you very much for watching. If you can, there is an arrow in the corner now pointing to a little doohickey that will help you subscribe to my YouTube channel. I am just one person doing these videos on my own. Very sad, very lonely sitting in a room, but hopefully for your benefit. So clicking that button really, really does help me. Now, as I normally do in my lessons, here is a recap. And as I said to you just a moment ago, we've been looking at flat rate depreciation, unit cost depreciation, simple interest, and all of these things, every single formula, if you remember, had a plus or a minus D. Now, okay, the last video, yes, we ramped it up and I gave you one example here where we were basically changing the formula ever so slightly from the idea of the next term is given by the previous term plus or minus some sort of common difference or payment to, oh, we can find a value 20 years into the future if I wanted to, so long as I know my initial value plus the number of payments that I'm making times the actual payment. So again, this is what I explained in a previous video. If that made sense to you, absolutely awesome. But the great thing here, or the point of all of this, was it was simple interest. We were adding on or taking away the same amount every single time. But I'd get a little bit annoyed if, say, I had $1 million in the bank. And trust me, I don't. I can't even make it to 1,000 subscribers. Wow, because nobody wants to watch maths videos. Who wants to watch maths videos? If I had $1 million in the bank, and they gave me $20 a month in interest, I tell you what, I'd be a little bit annoyed. On the flip side, if I had $5 in the bank and they gave me $20 a month, I'd be quite stoked because I was quids in. Now, obviously, the more money we put in the bank, hopefully we would like more interest. And I don't know about you, but the more interest I get, I'd like to actually have some interest on the interest. I want to keep getting richer and richer and richer. And actually that is called compound interest. So when you're actually getting more and more and more each month, because you're getting interest on the interest on the interest on the interest, then it's called compound interest. And we love that. Well, we do if we're actually paying money into the bank. Fortunately, banks like to charge compound interest on mortgages and loans as well. So the problem is the more and the longer you have the loan, the more and more and more they charge you. Yes, thank you, banks. Greatly appreciated. Maybe. More on that in another video. So we need to now start to model the idea of not things getting sort of bigger and bigger in a linear, in a line, but what we call geometric growth. And geometric growth is when things actually start to curve. And I've got a great example for you here. So I've said here, using a graph, plot the points you get with the following recurrence relationship. All right. Now again, recurrence relationship, take the previous term, do something with it to get to the next term. So we got V0, same language. My initial term is 2. And it says to get to my next term, take my previous term and multiply it by 2. Now, obviously, I've written this slightly different. It says 2 times my previous term, exactly the same thing. So here is n, there is V0. Okay, so what do we do now? To get to my next term, I double it. That becomes 4. To get to my next term, I double it. 8, 16, 32, 64, 128. And to be perfectly honest with you, the longer you do this, the more and more and the quicker that will grow. Now, if we were to actually draw this on some sort of a graph, and this is my 0, 1, 2, 3, 4, 5, 6, and these are my values of Vn going up the side. All right, and I'm not going to make this accurate because hopefully you'll be able to see this. But when it's 0, let's say my value is at 2, let's down here. The next one is at 4, then it's twice as big, then it's bigger again, and then it's bigger again. And what you get is you actually get a curve that goes on to infinity and beyond. In a later video, I'm actually going to show you how to be a millionaire. It's not difficult because all you need to do is pay in $6,000 a year, 10 years into a bank account, and you are done. Leave it, don't touch it, not for college, not for a car, not for a wedding, not for anything. And by about the age of 54, you will be a millionaire. You can give up work and live the life of luxury. Probably not, because $1 million, sadly, nowadays will only just buy you a house. Where did that come from? That is obviously a graph for growth. What do we notice? That was my initial value. As my value of N increases, so does my value of Vn. So I'm growing, thank you very much. But sadly, what goes up must come down. And in the same way, we can actually have geometric, oh, get my hands the right way around for the camera. We can have geometric decay as well. So again, I've got an idea here now that actually shows geometric decay. Watch what happens. V of 0 is equal to 2,000. And we know that to get to my next term, take my previous term and multiply it by 0.5. Now that just means halve it, divide it by 2. Now this is going to get a bit challenging in my head. So get used to my calculator. Get ready, calculator. So why are we multiplying it by a half? Watch what happens. The first value we said was 2,000. What is a half of 2,000? It is, thank you very much, 1,000. And what is a half of 1,000? We know it's 500. And half of 500 is 250. Half of 250 is 125. And now I'm going to fire up my calculator and I'm going to say, well, can you tell me what 125 times 0.5 is? And it's 62.5. And then I'm going to fire up my calculator again and say, can you times that by 0.5 as well for me to give me 31.25? 31.25. And if you're out there saying, really, you couldn't do that in your head? Well, actually, yeah, I could, but this is a CAS course. And the more you use your CAS to practice this type of stuff, hopefully the less chance you have of making mistakes. All right, that was a bit simplistic. I get that. But, yeah, I wanted to use it, so stop judging me. Again, here is my value of N going up, and here is my value of V of N. And 0, 1, 2, 3, 4, 5, 6, and these are all my values coming down. So let's say that was 2,000. This one would be half, this one would be half, this one would be half, and half, and half, and half. And once again, ladies and gentlemen, what do we notice? Well, it's definitely not a straight line. So it's not linear. And when it's not linear, we call it geometric. So in this case, this would be decay or linear decay. Oh, sorry, geometric decay. That's horrible. So the question is then, well, what made the difference in the formulas? Well, hopefully that's still on the screen, but here we had V of N plus 1 was equal to 2 times V of N, and the one below it we had V of N plus 1 was equal to 0.5 times V of N. This value here made it grow, this value here made it shrink. And the trick is, if this value here is 1 or greater, we will always, not 1 or greater, if that value there is always greater than 1, we will grow. And if it is less than 1, we will always decay. If it's equal to 1, then trust me, nothing happens, it just becomes a flat line, because anything times 1 is 1. And that's going to come up quite important, really. Now, what's the general form of a recurrence relationship? Well, you can see it behind me on the screen, and it says to get to my next term, take my previous term and multiply it by some number. Now, notice that number stays the same. And how do we work out this value of R? Well, for interest, and generally speaking, because this is going to be a financial course and it's going to deal with all sorts of money, we use this as my idea. So we say that R is equal to 1 plus my rate of interest divided by 100. Why? Well, interest rates are given in terms of a percentage. And so in this situation, if I had 10% increase, then I would know that my capital R would be 1 plus 10 on 100, which is equal to 1.1. And we remember, we're trying to say that when values are greater than 1, we will grow, and when they are less than 1, we will decay. So this is just a funky way of taking interest rates and turning them into numbers when multiplied that will give me greater than 1 or less than 1. Now there's a bigger discussion behind this. I'm pretty sure I've done it in a previous video, so go back and watch that if you have. Otherwise, bang it in your summary book, and let's hope you just remember it. So the big thing here is we always need to know our start value V0. In all of those, to be able to get to next term and next term and next term, we must know what V0 is. So here's an example extracted from the Cambridge Further Maths Units 3 and 4 textbook series. Thank you very much, Cambridge. Awesome, greatly appreciated. The following recurrence relation can be used to model a compound interest. Now, what on earth is compound interest? Compound interest is where it grows and grows and grows and grows and grows. So it's a language thing that you must remember. Simple interest is where it's linear. Same amount goes on every month. So a compound interest investment of $2,000, that is my initial amount, paying an interest rate at 7.5% per annum. And here is my recurrence relationship. Ooh. Use the recurrence relationship to find the value of the investment after 1, 2, and 3 years. Well, let's just check where they got that first. Remember, we know now that V0 is 2,000, but we were told that V of n plus 1 is given by V of n times some value of r, where we knew that r was 1 plus the little r over 100. Well, do we know what the little r is? Yes, it's 7.5. So r is equal to 1 plus 7.5 on 100. Fire up my calculator and let's just check that that's true. 7.5 divided by 100 gives me 0.075. Let's add 1 to that, which gives me, oh look, 1.075, and that was given in the question. So they've done the hard work for me. Thank you very much, Barry. So use the recurrence relationship to find the value of the investment after 1, 2, and 3 years. So I'm going to bring up my calculator again, and this is where this execute button comes in really handy. So the first thing I'm going to do is I'm going to put in my initial value and press enter. Now what I'm going to do is I'm going to times that by 1.075, and do you notice how my calculator is coming up with the ANS keyword? What it's saying is take my previous answer, multiply it by 1.075 and give me a new answer. It's the calculator doing this recurrence relationship for me. So hitting it once gives me the value after 1 year, 2,150. Hit it again, gives me the value after 2 years, 2311.25. And one more time gives me a great answer of 2484.59375. Now, words to the wise here, this is money. And I don't know about you, but I cannot walk into Coles or Woolies or any store in the world and see anything priced for $2,484.59375. So when it's money, you must make sure to round to 2 decimal places. So in that situation, if I wanted to do my answer to part A, I would write down in dollars $2,484.59. Now, why is it 59? Because the 3 that follows that 9 will not change the 9, and we leave it exactly at that. Oh, thank you very much. Determine when the value of the investment will first exceed $2,500. Okay, so here's part B. Well, we can just use my calculator again. Determine when the value of the investment will first exceed $2,500. Well, we're close. After 3 years. So if I press it again, does it go over $2,500? Well, I should cocoa. So nicely, my calculator's done it for again. So I'm just going to say after 4 years. Yeah, because after 4 years, it got to, what was the value again? $2,670.93. Doesn't matter. Write down the recurrence relation if 1,500 was invested at a compound interest rate of 6% per annum. Well, they're just basically changing the question. So they're saying, well, in this situation, V0 would be equal to 1,500. So what they're now asking us to do is to write a formula like this, but for the information they've given me. So I'm going to do a comma, and I'm going to say V of n plus 1 is equal to V of n times, well, we've got to work out this our version of 1.075. So what do? We know that this R value, this value here that we're looking for, is given by 1 plus the rate 6 divided by 100. Firing up my calculator, thank you very much. 1 plus 6 divided by 100 gives me 1.06. And so there we go, R is equal to 1.06. And I'm just going to put this back into my equation here. So I could rub that out and put 1.06. But once again, do you notice in the question, they put that number first, then times V of m. So just to make sure, because I don't want to lose any marks and I don't want the examiner to think I'm a numbnut, is equal to 1.06 times V of n. And ladies and gentlemen, there is my mark. Now, believe it or not, oh look, there's another question. How exciting, another question from Cambridge, and there's more to come. So, extracted from the Cambridge firm, Brian borrows $5,000 from a bank, and he will pay interest at a rate of 4.5% per annum. Really important here is that per annum. That means per year. Questions in the financial maths are really not that difficult, I promise you, but what they do try and do is they try and trick you, and this is one of the tricks here. And fast forwarding, they're going to ask you about yearly, quarterly, and monthly. Be very careful with that wording. So let VM be the value of the loan after n compounding period. Now, compounding period is effectively when they're paying interest. Write down a recurrence relation to model the value of Brian's loan if interest is compounded A, yearly. All right, so first things first. A, yearly, we know the recurrence relation starts V0 is equal to, the original amount was $5,000. I'm going to do a comma. VM plus 1 is equal to, well, I'm actually going to write R times V of n. And I'm going to change, oh, Darren, your handwriting today is shocking. So I'm going to work out the value of R. R is equal to 1 plus R over 100. Now, because we're dealing with yearly, my yearly interest rate is 4.5. So 1 plus 4.5 on 100 gives me, well, I'm going to fire up my calculator, but I actually already know this one. So 1 plus 4.5 divided by 100 gives me 1.045. And so I'm going to replace that R with 1.045 times V of n. And yay, whoop whoop, I'm done for my yearly. And here's the trick now with quarterly, and they love this trick. I'm getting 4.5% per year. So what interest am I getting per quarter? Well, let me think. How many quarters are there in a year? There are 4 quarters. So actually, when I'm going to try and work out my interest rate per quarter, I'm going to do 4.5% divided by 4. So 4.5 divided by 4 gives me 1.125%. Now, that is my percentage, but what's my value of R? Well, V0 is equal to still $5,000. My initial investment hasn't changed, but my V of n plus 1 now becomes equal to, well, I've got to work out a new value of R. I can't use the previous one. The previous one was for a year. Now I've got to use my quarterly interest rate. So that becomes 1.125 over 100 plus 1. No, not H. Try that again. 1 plus, fire up my CAS, 1.125. I've already got that value there. Divide it by 100, add on 1. And add on 1 gives me 1.01125. Wow. 1.01125 times VM. There we go. There is my recurrence relationship. Now, quarterly. Do you see what's going to happen for monthly? Well, again, remember our interest rate was given as 4.5% per year. So how do I work out monthly? My monthly becomes 4.5% divided by 12. Firing up my CAS, 4.5 divided by 12 gives me 0.375. 0.375%. And I know I'm going to have to work out my R value to give me 1 plus 0.375 on 100. So let's take that value, divide it by 100, press enter. And ooh, that value looks disgusting. That's your calculator trying to show off. Add the 1 value gives me 1.00375. So V0 is 5123, comma. VM plus 1 is equal to, oh, no, hold on a moment. My computer is lagging just a little bit. Don't know why. So V, let's try that again. V of n plus 1 is given by 1.00375 times V of n. Hopefully that is going to catch up with me before Christmas. It would be really useful. And there we go. There's my answer. And what we've said, remember earlier, is what goes up can come down. Our values that were greater than 1, see what I've written here, gave me that growth. Our values less than 1 gave me a decay. We don't like decay. So we need to be very careful now when we're dealing with decay that our formula slightly changes for R. When we are decaying or depreciating or whatever else, we need to make sure that our R value isn't 1 plus R over 100, it's 1 minus. And here's a great example. The rest of the formula stays exactly the same, but I haven't even read the question yet. Do you know the first thing my eyes have been drawn to is that value there, 0.93. Is it greater than 1? Is it less than 1? It's less than 1. So I'm now going to have some form of decay. V0 is my start amount. VN, we've got this. So we've got furniture purchased at $6,900. It's depreciating. Oh, depreciating. That's a word that in my head, the second I see it, I know I've got to do the minus. At a rate of 7% per annum. Okay, 7% per annum, 0.93. Let's just check that. R was equal to 1 minus 7 on 100. And bring up my CAS calculator. 1 minus 7 divided by 100 gives me, 0.93. Thank you very much. Just checking. Wanted to make sure that there wasn't a mistake. So, part A. Use the recurrence relationship, or relation, to find the value of the office furniture correct to the nearest n after 1, 2, 3 years. Again, didn't we just do a question like this? Right, well, let's fire up my calculator. We know 6,900. Press enter. That was my start amount. I'm now going to times that. Oh, there's my ANS, 0.93. Now, I've done 0.93. Let's make this proper. Let's do it 0.93. Won't make any difference, but it looks nicer. So, hit it once. There is the end of my first year, $6,417. There is my second year, $5,967.81. And there is my last year, $5,550.06. Now, I'm not going to write these down. They're there on the screen for you, but beautiful. Calculator's doing all the hard work for me. Thank you very much. Oh, actually, let's write it down, because when you do notes, you'll want to do this. So after the first year, what did we say? We said 6,417. After the second year, we had, wow, my handwriting is really bad today, $5,967.81. And the third year, come on, calculator, don't go quiet on me, is $5,550.06. Now, when I'm doing these questions, hopefully you're doing them on your calculator as well to check that you actually know all the keys. Part B. Determine when the value of the investment will first be less than $5,000. Let's do that. All right, so we've already got 3 years shown on my calculator. Hit it again. 4 years and 5 years. So 5 years. After 5 years, the value of my investment is $4,800. So it's after 5 years. Let's just put 5 years. Thank you very much. And let's move on to part C. Write down the recurrence relation. Do you see what's doing here? Very formulaic, all very repetitive. Write down the recurrence relationship or relation if the furniture was initially valued at $7,500. So V0 is 7,500, comma. At a reducing balance rate, reducing, going down, thank you very much, of 8.4% per annum. So we now know that that is V. Then plus 1 is equal to, we need to find this value of R. We know that R is equal to 1 minus R over 100. Why is it minus? Because it's reducing. So R is 1 minus the rate of 8.4 divided by 100. Bring up my calculator. 1 minus 8.4 divided by 100 gives me the fabulous value of 0.916. So R is equal to 0.916, which means that this becomes 0.916, make sure my point is there, times V of n. And we are done, ladies and gentlemen. There is no more to be shown on this particular version. Sorry about my screen earlier. Apparently was having a bit of a moment. My calculator crashed and I had to reboot everything, but really good to see you. It's been a lesson on modeling geometric growth and decay. Lots more videos to come. Thank you so much for watching. If you haven't already done so, can you just click that doohickey over there to record? To record? No, to subscribe. I'm just me doing this on my own. So thank you very much for any help you can give me. Otherwise, there's a video loading it from the Further Maths course. I'm MaffsGuru, signing out. Looking forward to seeing you in my next video. Take care. Have a good day.